Here we're going to expand our idea of equilibrium to a rigid body, that is to say an extended object where the forces would be applied in more different places than just in a particle where they'd be all at the same spot. If we have a particle with zero net force acting on it, then that particle is in equilibrium. We've seen that before. Basically, if you have two forces acting against each other, they just cancel. If you have an extended object with zero net force, so you have two forces here that are canceling, this might be in equilibrium. This one here is in equilibrium. But in this situation here, the forces have the same magnitude, so the net force is zero, but the orientation of the forces, the way those forces are being applied, is not symmetric, and so this is not static equilibrium. This object is going to be in motion. In fact, it's going to have a net torque and a angular acceleration as a result. If an object is unconstrained, it will naturally rotate about its center of mass. We've seen this picture here where we have a wrench that is sliding across a horizontal table, and it is naturally rotating about this white dot, which represents the center of mass as it goes. If you have a constrained object, that object will tend to rotate about a hinge or some other fixed pivot point, like a balance or a fulcrum. If there is a net torque about any axis, that torque will cause an angular acceleration. We know from Newton's second law in rotational form that a net torque will cause an angular acceleration. If we want a rigid body to be in static equilibrium, which is to say if we want the object to have zero angular acceleration, then that means that the torque must be zero. If this term is zero here, then the net torque must equal zero, but any net torque about any axis will cause a angular acceleration. So the special case here is that the torque has to be zero about not just any single axis, but in fact about every possible axis. We don't have to calculate every axis, but what this means is that any axis of rotation that we pick is sufficient for us to look at the torques and to find static equilibrium for an extended object. So to extend what we have seen before for equilibrium, for a rigid body that's in static equilibrium, we can say that the velocity should be zero, the acceleration should be zero, just as we've seen before, but now that it's a rigid body, we have this added requirement that the angular acceleration must also be zero, so that the object is not moving and also not rotating. To meet these conditions, the body must be at rest. That's what we mean about the velocity being zero. We said that the forces acting on it must give us zero net force, and we split that up in the x and y directions. That gives us the acceleration there. And then now we have this new requirement that the torque must be zero, so that we have zero angular acceleration as well. One thing to note here is that if you have a hinge or a pivot point, you have some object like this beam here is supported by a hinge. Basically, you have a pin going through the middle of the beam here, and this beam could want to move in any direction. And however it wants to move, that pin is going to hold the end of the beam in place and not allow it to move. So this pin in this hinge is going to apply some net force to the beam that basically is going to cancel everything out and make the net force equal to zero. But that can be kind of complicated, especially to find some arbitrary unknown force. So what I always do is I always assume, instead of one single force, I just assume the components. And I assume that there's a force in the x direction, a normal force in the x direction, and a normal force in the y direction, which are the reaction forces from this hinge, from the pin. However the end of the beam wants to move, the hinge will push back the opposite way. I always assume that they're in the positive directions, and they just fit right into the x and y components. And so what we want to do for static equilibrium is to assume no net force and no net torque, that these quantities are zero. That's not to say that there are no forces acting, but that the forces sum up to zero and the torques also sum up to zero. Then we'll draw a picture of the system, determine the object or objects of interest. In this case, we're going to be considering an extended object with different forces acting on it in different points. We'll identify the forces using the process we've seen before, but in this case, we want to make special note of the orientation of the force and also its distance from the axis of rotation, right? We need to know the direction and where that force is being applied. We also want to look at pivot points and compute the torques, how much torque is produced by each force about a given pivot point. Usually we're going to have a natural pivot point, which would be a place where there's a support, perhaps the center of mass, or a hinge or a pivot that forces the object to rotate about a certain point, or in general, the location of an unknown force. And what we'll do is apply Newton's second laws in linear and rotational form. You should start with Newton's laws in linear form. These are the simplest equations. Typically, these aren't going to be sufficient to get you your answers, but these are going to be the simplest equations and the easy ones to start. And then you just start adding torque equations, sum up the torques about one axis, sum up the torques about the next axis, sum up the torques about the next axis. Since the torques must be zero about any single axis, it doesn't matter which one you pick. And if you have a system of equations where you have multiple variables you're trying to solve, you can just add more and more torque equations, as many as you need, until you have as many equations as you'll need to find all of your unknown quantities. So to see this in practice, we can go back a step here. Here we have a beam. We already have our picture. The beam here is our object of interest. Sometimes we'll have other objects hanging from or sitting on the beam, but the idea is that if the beam collapses, everything else goes away as well. So the beam here is our object of interest. Then we want to identify the forces acting on the object of interest. We'll do what we've done before. Use our force ID process. We have a point of contact here. There's going to be a tension in this rope. We have a point of contact here with the hinge, and so there's going to be one two-dimensional force from this hinge, but instead of thinking of this as one two-dimensional force, we're going to think of it as the x and y components of that normal force from the hinge. And then the beam will also have a center of mass, and the weight of the beam will tend to act at the center of mass. We also have a pivot point here. In this case, our natural pivot point is just the hinge. If the beam is held in place at that end, then that's the natural pivot point for us to consider. And so now we can start applying Newton's second law. We have forces here in the x direction. We know that the forces in the x direction have to sum up to be zero. We have a tension force in the x direction that's pointing to the left, so that's negative. I have a reaction force from the hinge that's pointing to the right. Those are my only forces in the x direction, so those must be zero. In this case, I don't know my normal force. I also don't know my tension. There's no way for me to find either of those forces directly. Those are all forces that have to be found based on other forces that are applied in the system. So I can't go any further. I'm going to look in the y direction. Looking in the y direction, I have my normal force from the hinge pushing up. I've got the weight pushing down. Those are the only forces in the y direction, so that's also zero there. In this case, typically I'll know my weight, so I could find the normal force there, but I still have two unknowns. I have no way of relating either of them. So my third step is to look at torques. I'm going to look at the torque about this axis here. This is the natural place to look. The other reason to look here is that I have a torque due to the x component of the normal force. I have torque due to the y component of the normal force. I have torque due to the weight of the beam and torque due to the tension. The sum of the torques is going to be the sum of the torques produced by the four forces in the system. But for these two here, the distance between the axis of rotation and where that force is applied is zero. And so these two terms here for the two normal forces just go away. That's why we often pick our pivot point or our axis of rotation where we have these unknown forces, because if we're measuring the torque from this pivot point, the distance between the pivot point and where those forces is applied is zero, and so these terms just go away. In this case here, this is our phi for the weight. This is our phi for the tension. Notice that this is 30 degrees there. This would be 60 degrees. So this would be 120 degrees. And so we can go through and say the torque from the weight would be the distance to where the weight is being applied. This distance would be half the length of the overall beam. The center of mass would be at the halfway point. So we can call that L over 2 would be half the length. The weight is the weight of the beam, and we said that we've got a sine of 120 degrees there. The weight pulling down this way is pulling in the clockwise direction, so that's going to be a negative torque. Then we have the torque from the tension. The distance between the pivot point and where the tension is being applied, that's the full length of the beam. So we can call that L, the length of the beam. The force is the tension in the rope. The value of phi we have there is 150 degrees, and this force pulling that way is going to give us counterclockwise rotation, which is going to be a positive torque. In this case here, you can see how you can use the weight to solve for the tension. Once you know the tension, you can find the normal force and go on from there. So this is a application of this process of solving a static equilibrium problem for a rigid body.